Today we are going to discuss free body diagram, a vector diagram that represents all the forces acting on a body or system is called free body diagram. Today we'll be discussing many cases of free body diagram that arises in our classroom in our study in higher secondary level. When the body is in static or dynamic equilibrium, the sum of forces, the sum of net forces acting on the system is always zero. The forces along the horizontal direction and the sum of the forces along vertical direction is always zero whenever the body is in static or dynamic equilibrium. Let's discuss first case. Okay, horizontal motion, summation of block at rest. This body is at rest. Block at rest. Now first let's analyze the forces acting on the body. In this body, the weight mg acts vertically downward and the normal reaction acts upward. Normal reaction is the reaction force given by the surface to the body. Okay, since the body is at rest, there is no motion. That's why the sum of vertical forces, summation of Fy equals to 0. That's why it becomes R equals to mg simply. Okay, and there is no motion along horizontal direction. That's why we don't need to consider this. This is a very simple case. First case of free body diagram. Second case, block in uniform horizontal motion. Uniform, whenever the motion is uniform, block in uniform horizontal motion, the velocity is constant. And since acceleration equals to dv by dt, the acceleration becomes 0 in uniform motion. Here is a body in uniform horizontal motion. Let's discuss the forces on it. The weight mg acts vertically downward and the normal reaction acts upward. Now let's see the forces along x direction. Okay, this is applied force F and this is the frictional force acting in the direction opposite to that of force. Now we see along x direction there are two forces F and Fr. That's why F minus Fr equals to ma. And in horizontal direction there is no motion along horizontal direction. That's why summation of Fy equals to 0. That's why it becomes R equals to mg. Okay, here are the forces. These are vertical forces. R minus mg equals to 0 as we discussed earlier. And this is horizontal force. Summation of fx equals to ma. F minus fr equals to 0. If we assume since the motion is uniform, acceleration is 0. That's why F equals to Fr. If frictional force is also 0, then F equals to 0. It becomes Newton's law. Case 3. When a body is in motion with some acceleration. Now this is the case when the acceleration does not equal to 0. Previously we discussed the case in which the acceleration was 0. Now we are going to discuss the case in which acceleration is not equal to 0. Body moving in horizontal surface with some acceleration. Okay, this is body and this is moving. The normal reaction acts upward. The weight acts vertically downward. Okay, this is the direction of applied force. And A has some value. This has some value. And this Fr is the frictional force acting in the opposite direction. Now, in horizontal direction, summation of Fx equals to max. That's why what are the forces acting along x direction? F and Fr. That's why F minus Fr equals to 0. Sorry, F minus Fr equals not equals to 0 but equals to ma because acceleration is not equal to 0. F equals to ma if frictional force equals to 0. For vertical motion, there is no vertical motion. That's why summation of Fy equals to 0 and simply it becomes normal reaction equals to weight. That is R minus mg equals to 0. Now case 4, body at rest on inclined plane. This body is at rest on inclined plane. Now let's see the forces acting directly on this body. Weight mg acts vertically downward. Now, normal reaction acts normal to the surface. While drawing normal reaction, we must make here the angle here 90 degree. Students are found drawing haphazardly. They show normal reaction in this way, in this way, this way. This indicates unclear understanding. Normal reaction is normal to the surface. This angle should be 90 degree. Normal to the surface. Normal to the surface. If we produce this, we see here 90 degree. This weight mg has two components, two rectangular components, mg sin theta and mg cos theta. This angle, if this angle is theta, this angle is also theta. If we produce here up to here, this angle is 90 degree. The sum of this angle, and this angle is 180 degree, and this angle is 90 degree. By geometry, we get this angle as theta. Okay, now the body is at rest. Frictional force acts in a direction opposite to motion. This mg sin theta, the component of weight mg sin theta, tries to give motion downward. Meanwhile, the frictional force Fr comes into play immediately. Frictional force Fr. Okay, now along inclined plane, let's say this is x-axis, this is y-axis. Along inclined plane, the body is at rest. The body is at rest. That's why there is no motion. Mg sin theta minus Fr equals to 0. Fr equals to mg sin theta. Along y-axis, simply R equals to mg cos theta. This R and this mg cos theta, they are equal. Since the body is in equilibrium, we write R equals to mg cos theta, or R minus mg cos theta equals to 0. Simply R equals to mg cos theta. Force applied at an angle with the horizontal. A mass m is kept on surface, and the force F is applied at an angle theta. This is the case when you pull suitcase in the airport. Okay, this is our suitcase. We pull here, we are here. We pull this suitcase while carrying our luggage in the airport, and this is the angle theta. This is the same case here. Now free body diagram. Okay, these are the forces acting on the body. Let's see it once again. Okay, here is body, and we have applied force F at an angle theta. The weight mg, the body is lying on the surface. The weight mg acts vertically downward, and the normal reaction acts upward. And this F has two components, F cos theta along x-axis and F sin theta along y-axis. And this is the direction of motion. That's why frictional force Fr comes into play in this direction. For horizontal motion, simply it becomes F cos theta minus Fr equals to max. F cos theta minus Fr equals to max. For vertical motion, in vertical direction, there are two forces, R plus F sin theta. They are in the same direction. That's why they are added. And this mg is in opposite direction. That's why we take the sign of one plus and sign of next minus. F sin theta plus R equals to mg. R equals to mg minus F sin theta. Body is smooth inclined plane with horizontal force. This is the body. The weight mg acts vertically downward. Normal reaction acts normal to the surface. Mg has two components, mg cos theta and mg sin theta, as we discussed earlier many times. Mg sin theta and mg cos theta. These are rectangular components. The force F is applied horizontally, according to our question. Now, this force F, this is the main part here. This force F has two rectangular components. F cos theta and F sin theta. Okay, these are rectangular components. Along inclined plane, there are two forces, mg sin theta and F cos theta, and the body on smooth with horizontal force. Summation of Fx equals to max. F cos theta minus mg sin theta equals to max. In y-axis, summation of Fy equals to may, and since there is no vertical motion, the acceleration in this direction equals to 0. R minus mg cos theta minus F sin theta equals to 0. Body is placed on an inclined plane and force F is applied on the body at an angle phi with the inclined plane. Here is body and the force F. This force F is applied with some angle here according to the condition of question. Now, as usual, weight mg acts vertical downward. This mg has two rectangular components, mg cos theta and mg sin theta. Normal reaction acts normal to the surface. Now, F has components F cos phi and F sin phi. This acts along x-axis and this acts along y-axis. F sin phi and F cos phi. Now the surface is smooth, that's why we take frictional force 0. Now parallel to inclined plane along x-axis, summation of Fx equals to max. Let's write the forces in x direction. They are F cos phi and mg sin theta equals to max. Now along y-axis, summation of Fy equals to may. There is no vertical motion. That's why Ay equals to 0. That's why we can write this. If F cos phi is greater than mg sin theta, the body accelerates up. If this force is greater, the body will be moving upward. And if F cos phi is less than mg sin theta, the body moves downward. Which force is greater? Whatever force is greater, the body moves in the direction of greater force. Okay, two blocks of mass is M1 and M2 placed side by side on a smooth horizontal surface. We will be taking frictional force equals to 0. When a horizontal force F is applied to M1, the system accelerates together. Okay, the horizontal force F is applied and the system M1 plus M2, move together. Now, in here, what we need to understand is that the main point here is this is M1 and this is M2. This M1 exerts normal force on M2 and in the same time M2 exerts normal force on M1 as well, which are equal in magnitude and opposite in direction. Okay, R1 and M1G. Okay, what is this F? This F is the applied force. And what is this Fn? What is this Fn? This Fn is the normal force given by M2 on M1. We are taking all the forces acting on M1. And this Fn is the normal force exerted by M2 on M1. Force on M1. Now this is normal force on M1 by M2, as I discussed earlier. Now for M2, the main point students need to understand here is that this force F is not acting here. Students do mistake here. Consider forces acting on M2. Weight acts vertically downward and the normal reaction in the upward direction. Now, M1 exerts normal force on M2. and the magnitude of this force is equal to Fn. Okay, free body diagram we can see now clearly. Let's write the forces along x-axis and y-axis separately for masses m1 and m2. F minus Fn equals to m1a, Fx equals to m2a. Okay, let's add these two equations. We get the value of acceleration. Okay. Now this force F is applied. This is horizontal, and this force is applied with angle theta here shown in the diagram. Okay, now for M3, this is horizontal. Here, the force is applied in this way. F, this angle is theta. That's why this component becomes F cos theta, and this component becomes F sin theta. Okay, F cos theta and F sin theta. Weight all the time x vertically downward. Now, what is this N2? What is this N2? This N2 is the normal force exerted by M2 on M3. In the same way, M3 will also be exerting the same normal force on M2 as well. Okay. Along x-axis, R3 equals to this much. Now for mass M2, weight, normal reaction. Now the main important point is that this N2 is exerted on M2 as well. N2. And this M1, this mass M1, since the mass M2 were in contact like this mass M1 also exerts normal force on M2, and M2 also exerts normal force on M1 as well. N1. Okay, now let's write equation for x-axis and y-axis. We can write it very easily. Now for M1. Now this N1, the masses were like this. M3, M2, and M1. This is the normal force. Weight, this is weight. This is normal reaction R1. Okay, N1 equals to simply M1A. And for vertical direction, R1 equals to M1G. Okay, the total mass here is M1 plus M2 plus M3. Now, according to Newton's law, F equals to Ma, and the horizontal force here is F cos theta, which is the net force along horizontal direction, and the body is moving along horizontal direction. That's why we take the net force along horizontal direction only. A equals to this much. In this way, you can find the expression for or magnitude of acceleration while solving problems for M1, for M2. Says M1 and M2 with M2 greater than M1. M2, in our case, M2 is greater than M1. Here, we are taking frictionless pulley. There is no friction, and massless string. There is no mass of string. The accelerations of the connected masses are related equal in magnitude for a single string over a pulley. The tension in a massless, inextensible string is same throughout. Okay, the weight M2G acts vertically downward. Now, the tension T in the string. The magnitude of tension here, this and these are same because the string is massless and the pulley is frictionless. That's why tension throughout is same. The tension throughout is same. Okay, M1G and R, frictionless pulley. Okay, now there is horizontal motion for mass m1 and vertical motion only for mass m2. We'll be writing equations accordingly. Okay, this is the tension in the string. The tension always act away from the body. Acceleration is rightward. Now free body diagram of m1. Now summation of fx equals to m1a, and that's why t equals to m1a. Now for m2, the direction of acceleration is downward. That's why we write m2g minus t. If the direction were upward, we would have written t minus m2g. Since the motion is downward, we'll be writing m2g minus t. Summation of fy equals to m2a, m2g minus t equals to m2a. Now this is mass m3 kept on smooth surface, and two masses m1 and m2 are hung in two sides with frictionless pulley like this. Now this is massless string, and this pulley is frictionless. That's why tension throughout here. The tension throughout here is same. In the same way, this is massless string, and this is frictionless pulley. That's why tension throughout here is also same. The weight act vertical downward. Tension T2. Here the tension T2 is acting away from M2, and here tension T2 is acting away from M3. Similarly, tension T1 is acting away from M3, and here tension T1 acting away from M1. Okay, now let's see three masses separately. For mass M3, you can write T1 minus T2 equals to M3A, and R3 equals to M3G. For mass M1, M1G minus T1, the body is coming downward. That's why M1G minus T1 equals to M1A. For mass M2, T2, the body is moving upward, the body is going upward. That's why T2 minus M2G equals to M2A. M2 is kept on inclined plane and suspended, and the mass M1 is suspended in another side with through frictionless pulley. Now weight M1G act vertical downward. Vertical downward. The tension acting away from the bodies which are equal. The tension in the string is same as pulley is frictionless. This mg has two components, mg sin theta and mg cos theta. Exactly, we need to write here m2, not m1. m2. This is also m2. Okay. Also m2, and this is also m2, and this is also m2. Normal reaction. The direction of acceleration, rightward. Okay, let's see. Now, for mass m2, mass m2 is going rightward. That's why t minus m2g sin theta equals to m2a for x-axis. And there is no vertical motion. That's why r2 equals to m2g cos theta. And similarly for mass m1, there is no horizontal motion. That's why m1, this is m1, m1g minus t equals to m1a. On solving, we get the value of acceleration as this much simply by adding two equations. Okay, there is inclined plane, inclined at an angle theta 1 and theta 2. the masses M1 and M2 are kept in inclined plane and they are connected with massless string that passes over frictionless pulley. This is frictionless pulley. The massless string passes over frictionless pulley. Okay, weights are shown. And this M1G has two components, M1G sin theta 1 and M1G cos theta 1. Similarly, M2G has also two rectangular components. Let's write them. Okay. Now, let's write normal reactions, R1 and R2. R1 and R2. Tensions, T, act away from the bodies, which are equal. The direction of tension, acceleration is rightward. Now, in which side the body will be moving? In this side or in this side? If if M2G sin theta 2 is greater than M1G sin theta 1, the body will be moving rightward, which is our case. And if M2G sin theta 2 is less than M1G sin theta 1, the body will be moving leftward. But this is not our case right now. Okay. The directions of accelerations are shown for masses M1 and M2. Now, for mass M1, T minus M1G sin theta 1 equals to M1A along x-axis, and R1 equals to M1G cos theta 1 along y-axis. For mass M2, M2G sin theta 2 minus T equals to M2A along x-axis, and along y-axis, this R2. R2 equals to M2G cos theta 2. M2G cos theta 2. In the expression for acceleration, we can find by adding two equations. Three masses M1, M2, and M3 are connected together on frictionless horizontal table and pulled to the right with force F. Okay, there are three masses M1, M2, and M3, and they are pulled rightwards with force F. Yeah. Force is applied and the system moves with common acceleration. A is the common acceleration from F equals to ma, and total mass is m1 plus m2 plus m3. This is the value of A. Tensions in the string act away from the bodies. The common acceleration. Now, neither of m1 nor m2 nor m3 move with force F. The system as a whole moves with force F, not separate mass. The system m1 plus m2 plus m3 moves with force F. Okay, there is horizontal motion only, not vertical motion. For masses m1, m2, and m3, the directions of normal reactions and weights for different masses, for masses m1, m2, and m3, we can see no vertical motion. That's why T1 equals to m1a, T1 equals to this much. We substitute the value of acceleration here. T2 minus T1 equals to m2a for mass. F minus T2 equals to m3a. These are connected in this way, and all these strings are massless. Body is moving upward. Tensions in the rope act away from the body. Now, let's analyze this M1, this T1. In all the string, in all the masses, tensions are acting away from the bodies. Tension is a pulling force which acts on a rope, and we take tension away from body while solving problems. Let's see three masses separately. The direction of acceleration is upward. Now we are showing different forces on mass M3. Tension away. Weight acts vertical downward. Okay. Similarly for mass M2. Weight acts vertical downward. Now let's write the equation. We need to write only vertical motion. There is no horizontal motion. Okay, this is for M1. This is for M2. And this is for M3. Okay, two masses M1 and M2 are connected by massless string that passes over frictionless pulley, and they are suspended from rigid support as shown. When the masses are released, the lighter mass will move upward and the heavier mass will come downward. When masses are released, M1 moves upward and M2 moves downward. We have assumed M2 greater than M1. This is very simple and important case that is frequently asked in every exam. Okay, M1 went up and M2 is coming down. Okay, weight acts vertical downward. Tensions act away from the body. Now let's consider free body diagram. For M1 and M2 separately, there is no horizontal motion. The direction of acceleration for mass M1 is upward. The direction of acceleration for mass M2 is downward. T minus M1G equals to M1A. M2G minus T equals to M2A for mass M2. Let's add these two equations. We get the value of acceleration. And on substituting value of acceleration in any equation, we can get the value of tension. And this is the equation for tension. Okay. Here are forces, and some forces are taken into consideration and some forces not. We take only those forces which directly act on the body, and the different forces are given here. Okay, three masses M3, M2, and M1 are kept as shown. The force F is applied on mass M2. This is frictionless surface, smooth surface. All the surfaces are smooth. Now consider free body diagrams. M1, M2, and M3. For mass M1, M2, and M3, consider different forces acting on M1. Weight M1G is acting vertically downward. Normal reaction acts vertically upward. Similarly for mass M2, weight M2G acts vertical downward. Normal reaction upward. Sorry, there are two normal reactions, one by surface and one by another mass. Normal reaction. And this is the applied force. Now for mass M3, weight M3G act vertically downward. Normal reaction act vertically upward and downward as well. There are two normal reactions by two surfaces. There are the equations.